Hi, my name is Swarandeep Singh. I am a SQL Server DBA, Solution Architect and Data Engineer. Today, I'm going to give a quick demonstration on index optimization using execution plans. Indexes can be optimized even looking at joins and filters, though in case of very large scripts, execution plans are very handy. Before I get to the demo, I would like to share some knowledge about execution plans. What are the execution plans and why we need them in SQL Server? Why we need execution plans. Execution plans show how SQL Server will perform the process of extracting the data while executing a T-SQL query or batch. When execution plans are created, the execution plans are created when a query or procedure request is submitted to the query optimizer, and the query optimizer will then generate a query plan. What else? Also known as query plan, these are a set of steps that Query Optimizer calculates as the most efficient and low-cost way to access the data. Query plans are the roadmap defining how a query or procedure will be executed. How execution plans are created and cached. The process starts when a query is first submitted to the relational engine, where the query is parsed, syntax is verified. Once parsed, the result is passed to the query processor that divides the query into logical steps. These logical steps are translated into tree representation or sub-steps of the query execution. Next, relational engine verifies the objects, aliases, synonyms. If everything looks good, it is then submitted to the query optimizer. Query optimizer analyzes the statistics, I/O, memory, and CPU usage before creating the execution plans. Once execution plans gets created, SQL Server uses it to fetch the data, and it is also saved or cached for the future usage. What is the difference between actual and estimated execution plans? The estimated execution plan provides just the estimate of the steps SQL Server is expected to take to access or fetch the data. The estimated execution plans are generated based on saved plans. In the past slide, we have seen that when the execution plans are created, those are also cached. So those become the estimated execution plans. The actual execution is generated at runtime only. In other words, you have to execute the query to get the actual execution plan, and it contains real-time statistics about the execution. The actual execution plans are more accurate, but sometimes it is very difficult to execute the real query because the query might have been generated from front end or some other engine, and you may not know the parameters. So at that time, getting the estimated execution plans can be very helpful. Understanding execution plans. The actual execution plans can be set to be included before executing the query by pressing the shortcut command Ctrl plus M, or by enabling the icon from the toolbar as shown in the screen here. Execution plans are read from right to left or bottom right to top left. The execution plans can either be displayed in graphic, XML, or text format. The example that we see on the screen on the left side, that is a graphic representation of execution plan. The screenshot shows a typical execution plan with operators and line connecting between these operators. You may see multiple operators in the screenshot above, and each operator represents a step in the query execution. There are lines which are connecting these operators, and the thickness of these lines represent the volume of data or rows. These connectors actually are passed to the next operator. So you can get a visual feedback by looking at the thickness or thinness of the lines, how much volume of data is passed to the next operator. Similarly, each operator and line also have properties and will have information about query, predicts, indexes, estimations, and actual values in the property or data size in case of pipes or lines. When you open the execution plan, there are a number of operators, and each operator will have cost associated with them. And most common areas of interest that probably you will be looking at might be table or index scans, the pipes, thickness of the pipes, RID or key lookup, hash joins, nested lookup, operator properties. Screenshot on the left shows property of a clustered index, seek operator. Also, you can see different properties in the index seek, non-clustered, like estimated number of rows, actual number of rows, objects, output list, seek predicates, operator cost, etc. So in the screen here, you can see the mouse is hover over this task or this operator, and it shows some data here. So this data is very useful. The most common thing that you will be looking at: actual number of rows, estimated number of rows, the IO cost, operator cost, CPU cost. So, and also you will be looking at the objects, the list, output list, and the seek predicate. Operator cost is one of the most important property, as you can see here in this screen. It actually tells you how costly the operation was in the query. Output list shows over here columns returned from the object. Seek predicate shows the B-tree operation was performed. You can find out whether any column needs to be added in the index, a new index is needed, or covering index would be helpful by looking at these graphs. Pipes. A pipe is a representation of passing data or row to the next operator for further operations. A thick pipe shows more data in rows, and thinner pipe represents less data or rows. When you hover the mouse over the pipe, it would display number of rows data passed to the next operator as shown in the screenshot on the left. So this is the pipe, and when the mouse was hover over the pipe, it opens a pop-up window, and you can see here some of the properties. For example, actual number of rows, estimated number of rows, estimated row size, and data size. Let's talk about operators a little bit. While reading the execution plans, you probably need to understand different operators if you want to parse or understand the execution plan. It is difficult to cover all the operators thus. I would cover some of the most common operators here. The very first one is a select operator. This is actually the final result of the query. A clustered index scan. This operator actually tells you that a scan was performed over an index and could not satisfy the query request completely. Keep in mind that the scan is expensive operation than seek in most of the scenarios. Non-clustered index scan. It is very similar to clustered index. The only difference is it does not include all the data pages. It only includes the leaf level data. Clustered index seek. The operator shows that index meets the criteria of index and can access data set without scanning throughout the B tree. Non-clustered index seek. This is also very similar to clustered index, except that the only keys saved in the index are returned. Spool. Spool are a temporary set of data stored and can be reused by other operators' inputs. So these are a temporary set of processing while the execution plan was being processed, and the result can be used by some other operator. A key lookup. This operator is required to get the data from the cluster index when non-cluster index could not return all the columns, especially the covering indexes. RID lookup. This is very similar to key lookup, but the difference is that it is for the heaps instead of the cluster indexes. Merge join. This is one of the joining algorithm. This operator indicates comparing sorting datasets. It simply merges data based on matching values. Hash match. This is also a joining algorithm. This operator appears when joining two non-sorted tables. This indicates when indexes are missing, where clause with some calculation making it non-searchable, or you can say non-searchable argument. It uses bucket of datasets in hash tables, then compare the buckets. And the final one is the nested loop. This operator takes two datasets and joins them by scanning the outer set once for each row in the inner set. This is generally a low cost operator. So these three operators, merge join, hash match, or nested loop. These are used when you have a join, and the engine will decide which algorithm should be used. You can read more about all these operators from this link here. Let's see an example where I would demonstrate the use of the execution plan. These are the prerequisites. It should be, or I suggest should be, SQL Server 2014 or higher. You may also use a free edition like developer edition of SQL Server. For the purpose of demonstration, I'm using a very simple query here based on a test database which I have on my system. This query is selecting some data from two tables, a dimension table and the fact table based on the product key, and also there is a filter in the where clause where I'm getting the store key, data related to the store key. Let's quickly execute it. Before I execute it, let me tell you that these are the two options that I mentioned in my previous slides. Selecting this option will tell you the actual execution plan. You enable it, it will execute the query. Once the query is executed, it would display the execution plan, the actual execution plan. And this over here, this will show you the estimated execution plan. I'm sorry, this is the one which shows the estimated execution plan, and this will show you the actual execution plan. Let me quickly run this query here. So we have almost 200,000 rows. Let me add the execution plan. Let me run it again. All right. So in this result set, in the tab of execution plan, you will see the entire execution plan. Let's just ignore the message above which says missing index. SQL Server gives you a hint when it thinks that an index could help. It could be helpful if you are running short of time, you don't have enough time to think about it. You can sometimes use it, but I would highly recommend that do it yourself. Yeah, take help from it and do it yourself. In this execution plan, we have two tables, which are two scans. So one is index scan on the dimension product table, and another one is on the fact sales tables. If you click on this and look at the properties, you can look at some of the basic things like the CPU cost 0.93, the IO cost which was almost 14, the estimated number of rows 193,000 almost, and the estimated operator cost was 14.8, which is about 78% of the entire execution. There are some additional information like subtree cost or estimated row size, but I am At this point, I am more interested into looking at the predicate. The predicate is actually something that is very helpful in deciding the indexes. Here it is telling me that the predicate is nothing but a filter, the filter which I set here, where sl.store key in 200. 200 is the store key which I'm looking for. And also there are some output columns. So this is the column sales amount. You can see here, yeah, this column here. And sorry about that. So you can see the sales amount over here. You can see product key over here. And remember, this is the fact sales table, so that's why you are looking at the columns only from this table, sorry, this index. The other index, which other task or operator that we are looking at, is very similar. Everything is very similar, but this is not very expensive as compared to the previous one. You can compare it. It's almost 0%. So I'm not paying much attention to this one at this time. I'll review it if needed any attention, but right now looks like this is the highly expensive or the costlier operator, 78%. So what I want to do at this time is I want to go to my another query. So in this query, we notice that, yeah, one more thing I forgot to tell you. We noticed that we had two parallel operations. So these parallel operations are nothing but the parallel threads which were running to access the data or to complete the operations. And this was passed to the hash match, and finally the streams which were collected from these operators were gathered, and the select or the display, you saw the display, you looked at the result set at this point or here. So these parallel processes or parallel operators came because I have multiple CPUs and there are multiple threads available with the SQL Server. So it can utilize those threads to improve the process, to improve the operations. Now what happens if you only have one thread? So next query, what I'm going to do is I'm going to show you if I use max.1. The max.1 is nothing but tells that only one thread is required for this operation, the query which is written above. Now looking at execution plan, you notice that the parallel operations are gone. As compared to here, we have parallel operations. Here we don't. But it looks like it is much more expensive. If you look here, the estimated CPU cost is 3.74. The estimated CPU cost is 0.93, almost 1. So there is much difference. But other things like IO cost or number of rows or estimated subtree cost, almost same, not much different. It was just for the demonstration. Let me get rid of this. Now I'm gonna create one index. The index which I'm creating right now is very simple index. So I have two columns, store key, product key, and then I have covered column or covered index column, sales amount, simple fill factor 90 on primary. So how I decided I should use this. Let's go back to the query. In the query, I have store key filtration and I have filtration on the product key, and also I have one sales amount. Since the sales amount column is used in the select, I can use in the covered index or covered column or included column. But these two are used for the filters. This is the main filter and this is the filter in the join. So it is recommended that you put these into the main index, and then you include sales amount over here as a covered index column. You remember this was in the select. Let me create this. Okay, it's created, and let me go to this point, my third slide. I'm sorry, I didn't include the execution plan. So let me run it again. Okay, I got the execution plan. If you notice here, a couple of changes. The first change is, even though I didn't include max DOP1 option here, it didn't use the parallel operation. The second thing is it replaced the hash join with merge join. If you look at here, we had hash match joins. Looking at the cost, let's look at it. So over here, our CPU cost was 0.93 after creating the index that we created in the last step. The CPU cost is down to 0.21. The IO cost was almost 14. Here the IO cost is down to 0.51. And number of rows will remain same because we are not changing anything. The only difference you see here is it has much accuracy here, estimated number of rows. Over here there was a little bit off. It was a little bit off, 194 something and 193 something. Now let's see if we can further improve it. If you notice here, we have a filter, and this filter is static. So we are passing the fixed value 200, and if it is static value, then you can create a filter index. A filter index is nothing but you just enable filter on the index. The same option which I add here, I added here. Now let me drop my previous index. Let me recreate this index. And let's see if we see any difference. Let me copy it into a new window just to make sure we have our data not lost. All right, so we have now here much more improvement here on the IO cost. It is much better. The CPU cost is also dropped, and the operator cost is also dropped. The only thing I added, just to reiterate, I added a filter. So that's all. So we looked at how we can review the execution plans and take help from execution plan to write our indexes. Thank you.